So, yeah, thank you very much to the organisers for the invitation to tell you a little bit about what we do. There we go, there is Aberystwyth. So my name's David Whitworth. I'm predominantly teaching biochemistry in our Department of Life Sciences and also involved in accreditation. But one of the aspects of biochem that I'm particularly keen on delivering and developing is practical skills within the students, aiming at research career. And so I'm just going to give you a couple of examples of what is essentially PBLs that we do with our students to help them develop their practical skills. And it's going to be a bit of an echo from the comments from that table there in the previous discussion. The second one is anyway. But the first thing I'm going to talk about is something that we call our tutorial project. Now, we aren't the biggest or the smallest department in the country by any means. We have about 300 students per year, and we do have quite a lot of different degree schemes which spread the entire breadth of biology, agriculture to zoology, but most other things we dabble in as well, sports and exercise science, veterinary science, quite a range of different areas, which creates challenges of its own. And of course, we want to foster a culture of innovation and experimentation and creativity, but we also want to develop practical skills as well. And the challenge for this is that we need to deliver it to every student, even though they are on very diverse degree schemes. And we do it, therefore, using a first-year skills module. So this is a module which focuses on the development of academic skills and therefore is taken by every single first year. So we cover plagiarism, how to reference, those sort of core academic skills that they're going to need throughout the rest of their time. And that module, as well as having a little bit of didactic content at the beginning, is taught through tutorial groups. So every student is in a group of around 6 tutees led by an academic. And the academic will have regular tutorials during the semester with their tutorial group, fairly standard. But I guess what may not be so standard is that each tutorial group undertakes a research project within the first semester of arriving in the university. So like I said, this is in year 1, first semester. Each tutorial group has to come up with a project, do the project, and write it up as a lab report or as a report which is then assessed. And it's led by tutors because every student is assigned a tutor that's in their subject area. I will only ever have biochemists or microbiologists in my tutorial group, and similarly the animal behaviour people will only tutor students in that subject area, which means that we can allow the tutors to develop projects that suit their discipline, and necessarily that's going to appeal to the students in their tutorial group. Okay. We have a few requirements of the projects, but they're really minimal. So the projects have to generate numerical data, such that which can be plotted and which can be interpreted. So the ecologists generally were going to be doing t-tests and things like this. Biochemists tend to do more calculations and data that can be plotted. So in the assessment, we know that we can look at students producing graphs and make sure they're producing graphs properly, which they're going to need to do in all the rest of the reports. Okay. And through the tutorial system, it means that we can just run a huge diversity of projects. There's just some examples there in the bullets on the bottom right-hand side, but the effect of dog whelk predation on sea barnacles. The tutorial group goes down to the seaside and they measure the size of the barnacles and they measure the dog whelks and all that sort of stuff. The one I do, just as an example, is lab-based and determining the extinction coefficient or the absorbance of a dye. And it's a very straightforward thing to do. My job as a tutor is to make sure the students understand what we're going to do and why, and all of the terminology and things like that. And then we work together to plan what they might do in the lab. So I can then organize them in some way. So I might come up with there's a sort of a guide document there that I might put together for them after we've discussed it. And they're aware of the issues, but if you can read that, which you probably can't, it's really lacking in detail. So it's essentially just make up a solution, dilute it, measure the absorbance, calculate the extinction coefficient. But it means that when we then planning on going into the lab, when one of them asks for a 100-litre beaker, I can think, we might need to change that. It's kind of what they're going to be thinking about is the practicalities. How many tips are you going to need? How many repeats are you going to need? You say you want to make a 1 molar solution, but how are you going to make that? Is it going to be soluble? There's lots of things that we discuss as a group, but ultimately, I take them into the lab, give them whatever glassware is available, and they innovate, get it wrong, problem solve, do it again, and it's kind of, it's a bit of a free-for-all, but they're free to experiment and learn how to generate the data. And then the final tutorials just come together, we discuss the data, we show them how to interpret it, they write it up as a report. Lovely jubbly. Okay. So that's how the tutorial project works, and all of us do that. Now, I can't be here for this evening, but I have a colleague at the back, Peter Dennis, who runs his own tutorial projects, and I'm sure he'd be happy to talk about his. There we are. But the other thing I was asked to talk about is something where we get students to design their own protocols. And this is something in my module for second-year biochemists, and it's a practical skills module. The students do a series of practicals where I tell them how to do the experiment. It's a very traditional step 1, do this, step 2, do that, what have you. So they're comfortable with the idea of doing experiments. But the final task is that they have to develop their own protocol to solve a question. And the question is, measure how many atoms of iron there are in a molecule of hemoglobin. Okay. Now, the reason I chose that is because it was a practical I used to run. So it was a very straightforward piece of chemistry where I would take hemoglobin, oxidize it to release the iron, reduce the iron. It will then bind to ferrozine, which gives a colored compound, and we can assay the amount of iron through that. So we have some controls, proteins without iron, and just iron without protein. But ultimately, it's a very straightforward and simple experiment that I know can be done in a couple of hours. So decided to turn that into a task where the students design their own protocols, which they find absolutely terrifying. It must be said. So they need a lot of support, and I've put a lot of scaffolding into this task. And because it's based on a pre-existing practical that we used to run, I know exactly what materials they need, I know how much of each thing they should need. I have a list of materials that I tell them I'm going to provide them, because there will be some, if you just ask them to find out how much iron there is in hemoglobin, they say, well, first we need to just purify the protein and then solve the crystal structure. And you think, well, that would be a nice way of doing it, but perhaps we'll do a simpler way. So again, there's a bit of information about the color chemistry involved. We do all the hard work for them by providing reagents of the correct mixtures, the correct ratios, and we guide them on how to use those reagents. And the students, therefore, need to focus on other aspects of experimental design, the practicalities. What volumes are you going to use? So we can make sure they're not using too much of ferrozine, which is pretty expensive. But how many replicates are they going to do? What concentrations is their calibration curve going to cover? How do they know their hemoglobin sample is going to fit somewhere on that calibration curve? There's loads of things that you can discuss with them about very common aspects of experimental design. Now, we don't assess this practical how we assess the other ones. For the other ones where we give the protocol, it's a very standard. They write a report, we mark the report based on their results. Here, they don't write up their results. We assess the protocol itself. So that reduces the stakes in their mind, because they don't need to get it to work in order to get a good mark. If their experiment is rubbish, they can still do a nice job on the protocol and get a decent mark. So by reducing the stakes of the assessment, we're encouraging them to innovate, and they don't see it as so risky. But we have to timetable it carefully to provide support at key stages. So at the top, there's the timeline of how this is organized. We set the task, and they're terrified, and we divide them into pairs, pairs of pairs, so they have a shoulder to cry on at least. And they spend a week, perhaps, coming up with a general strategy for how their protocol is going to work. There's then a session where they get feedback from staff on that draft. So clearly, if they're doing horrendous numbers of replicates, or they're doing 10 samples in series rather than in parallel, those sorts of issues we can sort out before. There is then a prototyping session. So they will get to try their protocol out, and there's a 10% chance it will work at that point. There's then a week to reflect and evaluate and refine, and then they get a second attempt to do the experiment, and at that point 90% get it to work. So that works really nicely. But one thing we don't tell them is that for that first session where they get to try out their drafts, we collect all of the drafts in just to make sure that they're okay, health and safety-wise. And then we hand them back to different pairs. So they've arrived thinking that they're going to do their protocol, which they've worked on for 2 weeks. And suddenly, this guy they don't know at the back of the room is doing theirs, and they've got something that's really, they don't know what to do with in front of them. And it's ironic, because they're actually halfway through this at the moment, that prototyping. They should have probably recovered from having the protocol swapped and are busy getting on with it. But after that initial shock, panic, it does usually reduce a couple of people to tears each year. I think there's a mixture, and it's not just sadism that makes me do that, okay? They soon recover, the tears do stop, and they sort of understand why I do it, because a lot of the protocols are just written on the back of an envelope and extremely embarrassing to the person who didn't put in the effort to write it up nicely. But most of them will start by make up a solution of hemoglobin. And that will be step one of their protocol, and clearly it's completely inadequate. But they say, well, I knew what I meant, and I'm sure they did. But as a protocol, it's rubbish. So it exposes all those sorts of flaws, but it's in a non-threatening way. It's not me criticizing their piece of work, it's a peer. So they're all in the boat together. I'm the common enemy, so it actually increases collegiality. But as they're working through the methods as well, there's the opportunity to feed back. So I've got this rubbish protocol, I don't know what to do next. Well, we'll ask the person that wrote it then, he's just there. And they do. And so there's a real nice buzz about the lab. People in the group talk to each other who've never talked to each other before, and they're forced to, and they're learning from each other. They're desperate to know, did my protocol work? And here's how you can improve yours. And so I like it.